Welcome to the MedPhysio tutorial series, where we simplify physiology while keeping its depth and beauty intact. Today's topic is the resting membrane potential, the silent voltage that powers excitability. In this session, we'll explore what creates this resting potential, how it's maintained, and why even this resting state is full of dynamic regulated activity. This tutorial is designed to guide you step by step from the ionic basis to the functional significance of this essential physiological foundation. So let's begin. Every excitable cell, whether it's a neuron, cardiac fiber, or skeletal muscle, maintains a resting voltage difference across its plasma membrane, the resting membrane potential. Quiet electrical tension sustained by selective ion movements and membrane properties. This resting potential is the starting point for all electrical signaling in the body. Without it, action potentials couldn't be generated. Muscles couldn't contract, and the neurons couldn't transmit information. On the next slide, we'll define this resting membrane potential more precisely. At the end of this tutorial, you should be able to first clearly define the resting membrane potential, understanding what it represents and how it's measured. Second, describe how different ions contribute to the steady state voltage across the membrane. Third, explain the role of sodium potassium pump and membrane permeability and how their coordinated actions maintain the delicate balance of charge. Fourth, relate the resting potential to cellular excitability and action potential generation, because these baseline voltage is what allows excitable cells to respond swiftly when stimulated. And finally, we'll discuss clinical correlations. So keep these objectives in mind as our guideposts. Resting membrane potential is the voltage difference across the cell membrane of an unexcited or resting cell. In simple terms, this means that the inside of the cell is negatively charged compared to the outside, even when the cell is not actively firing. Typical values vary slightly between cell types. In a neuron, the resting potential is about minus 70 millivolts. The skeletal muscle fiber, it's even more negative, around minus 90 millivolts. Now, this potential arises from the unequal distribution of key ions across the membrane, primarily potassium, sodium, and chloride, along with impermeant intracellular anions, collectively represented as A minus that you see there. That's A raised to minus X. Now, these impairment anions, including large proteins, phosphates, and organic molecules, remain trapped inside the cell, contributing to the interior's negative charge. Exam tip: when defining the resting membrane potential, always mention both ionic distribution and selective membrane permeability. Both are essential components and earn marks in essay questions. Common mistakes that students make is they forget to mention the impermeant anions. Please don't leave them out because they are crucial to the negative internal environment. The resting memory potential is the result of a balanced set of physiological determinants. Let's look at each one properly. The first is concentration gradient. Potassium ions are far more concentrated inside the cell than outside. Because of this steep gradient, potassium tends to diffuse out through the leak channels. Intracellular, extracellular, more potassium ions diffusing out into the extracellular fluid. Now, this outward movement of positive charge leaves the inside increasingly negative, and this potassium efflux is the dominant force reshaping the resting membrane potential. Secondly, the membrane permeability. The membrane is much more permeable to potassium than sodium. Only a few sodium ions can leak inwards, while potassium continues to drift out freely. This difference in permeability is what makes the resting potential closer to the equilibrium potential for potassium than for any other ion. Now, as an exam tip, Always remember to write. The resting membrane potential is close to the equilibrium potential of potassium because the membrane is most permeable to potassium. The single statement shows conceptual understanding and earns full marks. Thirdly, the sodium potassium ATPase pump. This active transporter continually moves 3 sodium ions out and 2 potassium ions in for every ATP molecule that is hydrolyzed. By doing so, it preserves the ionic gradients and adds a small electrogenic effect, making the inside slightly more negative. Finally, negatively charged intracellular proteins, these large impermeant anions remain inside the cell and further reinforce its internal negativity. Now that we understand the qualitative determinants of the resting membrane potential, let's bring in the mathematics that describe how multiple ions change this silent voltage. The key equation here is the Goldman-Hodgkin-Haz equation, often called the GHK equation. It expands upon the simpler Nernst equation, counting not just for a single ion, but for the combined effects of potassium, sodium, and chloride, each weighted by the membrane's relative permeability to that ion. When we apply the GHK equation to a typical neuron, calculated resting membrane potential is about minus 70 millivolts. Notice how this value lies closer to the potassium equilibrium potential of potassium than to the sodium equilibrium potential of sodium. That's because, as we discussed, the membrane at rest is far more permeable to potassium than sodium. So potassium has the dominant influence. Now, to understand the resting membrane potential, we need to start with the surrounding foundation. Now, this is the unequal distribution of ions across the cell membrane. Inside the cell, the concentration of potassium ions is high, while outside, concentration of sodium and chloride are much higher. These gradients are actively maintained and form the chemical energy source for membrane voltage. Now, because sodium is more concentrated inside, it naturally tends to diffuse outward through potassium lead channels. Conversely, sodium being more concentrated outside tends to diffuse inward through its few available channels. But here's the key. The cell membrane is selectively permeable. And at rest, it is far more permeable to potassium than it is to sodium. This means that potassium's movement dominates, leaving behind negative charges that can't follow. Among these immobile charges are the negatively charged intracellular proteins. These reinforce the negative potential relative to the extracellular space, and so resting potential is formed as the result of an ionic imbalance maintained by selective permeability. The next slide, we see how the sodium potassium ATPase pump maintains these gradients and sustains the resting state against constant ion beats. Up to this point, we've seen how the resting membrane potential rises through diffusion and selective permeability. Those passive forces, if left unchecked, would eventually run down the ionic gradients. Potassium will continuously leak out, and sodium will drift in, and the membrane potential will fade away. To prevent that, cells employ the sodium potassium ATPase pump. This pump uses the energy from one molecule of ATP to move 3 sodium ions out of the cell, 2 potassium ions into the cell. Let's pause on that. 3 sodium ions out removes an extra positive charge from the interior, removes positive charge from the interior. And 2 potassium ion brings in back less positive charge than that which was lost. 3, 2, -1, right? The result is both a maintenance of ion gradients and a net negative effect on the inside. Now, this action serves two essential roles. Remember that normally sodium ion does not really, it has cannot really pass the membrane, doesn't really pass through the membrane, it has very, um, the membrane is poorly permeable to sodium ions. So the energy from the ATP allows these movement of sodium ions from the intracellular to the extracellular space. Now, this action serves two essential rules. One, maintains the concentration gradient for sodium and potassium, ensuring that the passive diffusion forces can keep generating the resting voltage. Two, counteracts the continuous passive leaks that occur through ion channels, keeping the cell in a steady electrical and chemical state. Importantly, this pump is electrogenic. That is, it contributes directly to the membrane potential by making the inside slightly more negative, roughly minus 4 millivolts of the total resting value. So while diffusion creates the resting potential, the sodium potassium ATPase sustains it. Now, after exploring how the resting membrane potential is established and maintained, let's see why it matters functionally and clinically. Resting membrane potential determines how easily a cell can be excited. In other words, it sets the excitability threshold, the starting voltage from which an action potential can be triggered. When the resting membrane potential, I use RMP, is stable and within its normal range, excitable cells such as neurons and muscle fibers respond precisely and predictably to stimuli. When the RMP shifts, even slightly, consequences can be profound. In hyperkalemia, where extracellular potassium levels rise, the RMP becomes less negative. The cell is partially depolarized. This brings the membrane closer to its threshold, but paradoxically, prolonged depolarization inactivates sodium channels, leading to muscle weakness and reduced responsiveness. In hypokalemia, the opposite occurs. Low extracellular potassium makes the RMP more negative or hyperpolarized. The membrane moves further from threshold and cells become less excitable, resulting again in muscle weakness and sluggish neural activity. Exam tip: always link the resting membrane potential to excitability and threshold potential when answering essay questions. These physiological connection demonstrates reasoning beyond memorization. So let's bring everything together with a quick recap of the key concepts behind the resting membrane potential. First, remember that the resting membrane potential is the potential difference across the membrane of an unexcited cell, and the inside is negative relative to the outside, even when the cell is at rest. Second, this voltage is maintained mainly by two forces: diffusion of potassium through leak channels and the steady work of the sodium potassium ATPase pump that sustains the ion gradients. Third, typical value is around minus 70 millivolts in neurons, which is closer to the potassium equilibrium potential because of the membrane's higher potassium permeability. And finally, this resting potential is what determines cellular excitability. It sets the stage for action potential initiation and ensures that nerves and muscles are always ready to respond when needed. So, the next time you think of an excitable cell, imagine this silent electrical charge, constant, balanced, and essential, quietly empowering every single signal, every contraction, and every heartbeat. To wrap up, let's consolidate what we've learned about the resting membrane potential and test our understanding with a quick quiz. Now, the key takeaways: one, the resting membrane potential arises from the combined effects of ionic concentration gradients and selective membrane permeability. Two, potassium plays the dominant role since the membrane at rest is most permeable to potassium. Three, the sodium potassium ATPase pump continuously maintains the ion gradients, keeping the cell in a steady electrical state. Four, the resting membrane potential sets the stage for action potentials. Starts, um, it's the starting voltage that defines excitability. Five, clinical changes in potassium levels, whether hyperkalemia or hypokalemia, can shift the resting membrane potential and profoundly alter nerve and muscle function. Now, let's reinforce these ideas with a quick quiz. One, question one: what's the normal resting membrane potential in neurons? Yep, ultimately minus 70 millivolts. Question two: which ion most strongly determines resting membrane potential? Both, I know it. You know it's potassium. Three, what happens to resting potential in hyperkalemia? Yep, it becomes less negative. Membrane depolarizes, moving closer to threshold. Good. Well, that brings us to the end of this MedPhysio tutorial on the resting membrane potential, silent voltage that powers excitability. We've now seen how a few key ions, a selective membrane and one tireless pump, work together to create the electrical foundation of life. This has been part of the MedPhysio tutorial series, Simplifying Physiology, where we make complex concepts clear, connected, and clinically meaningful. Thank you for learning with us. Remember, keep exploring, keep asking why, because physiology is life explained. Until next time, stay curious, stay inspired, and keep learning.